see. Let's make sure the mic's working. It wasn't earlier. Hello? Perfect. It looks like it is. All right. This course is the programming parts of this course aren't hard. I mean, that's a relative thing, right? Like maybe you do find it hard. I mean, they're not simple, but it's like the programming bits are not the parts that are interesting to me. What's interesting is the bigger picture ideas that we're going to talk and cover, okay? So this course is evolutionary computation. There is no 547 this semester. 547 is the graduate section of this course. It's not offered right now, so you're only 340, unless you're directed study. This is me. Yeah. All of my office hours, so those will be my office hours, but all my office hours are going to be held virtually this semester for the foreseeable future. The annex is terrible, and I don't want to get COVID, so we'll do it virtual for the time being. Yeah. So what's it all about? Well, we're going to talk about evolutionary computation. And part of evolutionary computation is evolutionary algorithms, and part of stuff under that is like genetic algorithms, genetic programming. There's a lot of like similar words being used that can get confusing, but you'll probably be fine. There's swarm intelligence, like particle swarm optimization, PSO, ant colony stuff. Really interesting algorithms out there. We're going to talk a little bit about how we can represent and encode problems and ways to, I don't know, give pros and cons. Common algorithm improvements like evolutionary computation algorithm improvements. In fact, the common ones that we're going to talk about for the most part that like I will talk about are going to be some of the old ones that everyone uses now, but like they're the older ones. But there will be an opportunity for students to give lectures. And that's where maybe, I hope we get more of the newer, interesting enhancements that people do these days. Application areas, search-based analysis, evolutionary neural networks, whatever. Oh yeah, and a big part of this is technical communication, both lecture and written reports. You don't have to do a lecture this time. And last year, 2 years ago, the lectures were mandatory, but at that time there was only 15 students. Now with like 45, that's not going to work. So not everyone can give a lecture. So it'll be by like volunteering, but I'll explain mark breakdown shortly. And all of you, raise your hand if I've taught you before. Okay, so you all know how I am, right? If you have a question, just raise your hand. You know how I am. Prerequisites, 255 and 223 or 275 or with permission. If you don't have the prerequisites, you're in trouble. Oh yeah, unless you have either written or whatever. This is the textbook. You can find it online for free. Sadly, it's old. It's not bad. It's really good. It is arguably the definitive one that everyone uses, but it's old. So it might not talk about some of the more recent, really cool things, but for our purposes, it's fine because we're starting down here, and remember big picture stuff. But yeah, you can find this online. It's pretty good. The slides that I have are somewhat based on the slides that come with that, but as a lot of you know, I also don't like lecture slides that come with textbooks. Moodle will have everything, lecture slides, assignments, the projects, links to things I think are cool. Check it frequently. Currently, I think I have like one interesting thing posted. Raise your hand if you've been to the Moodle page yet. Did anyone read iPencil? Well, yeah, that was before though. All right, I think I have something called iPencil posted on Moodle. It's a short read, but have a read. And maybe we'll talk about it next class, which is Thursday? Yeah? Okay. It's in my calendar, but I don't know. Lecture slides are available on Moodle. They're here to help because because I'm nice, they're not a substitute. Assignments and projects will be posted on Moodle. Submission details are posted there. Late assignments, if you've had me before, you know how I am. In on time or 0. If it's due at 11:55 and you submit at 11:56, is it in on time? No. Does it get marked? No. See, you all know. Assignments, they definitely will be marked by TA. And if you want to remark, there's like policies to follow. You have like a 2-week window. That's kind of flexible, but like if it's assignment 1 and then in December you're like, no, my son, I want it remarked, that's going to be a problem. Keep backup of everything. In today's world, the excuse of, oh, my computer crashed, doesn't really work because everyone uses cloud storage and everything these days. So make sure you're using that so you don't lose your stuff. Allowable languages. I don't care what programming language you use, really. These are, C# could be included here. These are the ones, like popular ones I would encourage you. But honestly, I don't care as long as you get permission from me first. One language I will not allow is MATLAB. Because 1, it's stupid. No. MATLAB is great for what it's great at. But also because it's not open. Like you need a license for it, so that's not great. So yeah, if you say to yourself, you know what, I really want to learn Go. So I'm just going to do everything in Go. All right, just let me know and I'll give you the thumbs up, cool. But other than that, I don't really care what language you use. Raise your hand if you think you'll use Java. 1? What? Oh, man. How about Python? Yeah, okay, I get it, yeah. C++? Okay, all right. C? I don't recommend C, actually. I should probably take that off here. You'll have a bad time if it's just C, probably. For those of you that don't know, 162 this year is in Java now. Yeah. You should check out CSCI340 if you want to have a look at how things go. It's there, FYI. Yeah, just check. Okay, here's how the marks are going to work. And I'm going to leave this slide and just go. All right, this is the same. So here's how it works. For the most part, so you know how like in classes, like, oh, you submit your assignment and you lose marks for every mistake you make or something, right? Like that's just how it's worked since you were this big. I'm throwing that out. What I'm doing is, there is some of that, kind of. But what I'm doing is giving you marks for stuff you do. You don't lose marks, you gain marks. It might seem like an arbitrary distinction, but it's not. For example, assignment 1. I will spend a good amount of time explaining this because it is unusual. So assignment 1, you can get a maximum of 30 points on assignment 1. If you get a genetic algorithm working for traveling salesman problem, you get 5 points. Now the funny thing here is, those 5 points, that's just, can someone just make sure that actually adds up to 30? Someone do that while I explain. The 5 points, great, but that's only 5 points. And that's the code part. I don't care about your code. At this stage, if you can't write working code for a GA, that's a bigger problem than me. So at this stage, if you get your stuff working and it's fine, I'm not going to look at your code. I might do a quick look to make sure you didn't cheat or something, but I really don't care about the code. What I care about is what you've done that is something that you gain, something that you learn from it. So for example, if you add interesting modifications from like a vanilla, for lack of a better term, genetic algorithm, but if you start adding these extra little enhancements, you can get up to 4 more marks. If you solve the more complex version of the problem called vehicle routing, you'll get another 5 marks. If you do some good visualization of your results, you get 2 more marks, or points, whatever you want to call them. And then there's the write-up. Did someone confirm it adds up to 30? Yeah. All right, good. I'm not crazy. I do have a bad habit of that, though. Having totals not add up because I make changes all the time. Your write-up. You don't have to do the write-up, but you'd probably be making a big mistake if you don't, because that's where you can get a lot of marks. is if you write your genetic algorithm and you get it working, great. You should be able to do that. The GA itself, the base thing, relatively simple. Not necessarily trivial, but not a hard thing to implement relatively. But what I care about is your ability to think about what you did, to tell me what you did, to tell me what you think about it, to explain why this worked and that didn't work and all that. I care about your ability to, one, it's big on technical communication, and two, you're basically going to be writing a scientific article. Now, it's going to be doing something like a basic GA, so it's not going to be groundbreaking. Maybe it will be. But I care about your technical writing, what your analysis is of your results. I don't care that you can code a GA. You should be able to do that now. I care about what you can tell me about it. And then on top of that, if you do it in LaTeX, raise your hand if you've used that before. You're lucky. If you write it in LaTeX, you get an additional 3 points. If you have good references and whatnot for your code, or for your write-up, like other scientific articles you include in reference, there's another 2 points. If you have good figures and tables, there's another 2 points. And if you do sufficient good statistics, I mean, I'm not talking about averages. If you do averages, you're not going to get any points. But if you do like reasonable statistical analysis of your results, there's more points. So you can get a total of 30 in assignment 1. Now, the write-up, the refs, the figures, tables, the stats, that marking is going to be a little bit more subjective. That's where it's going to be like, okay, well, how, you're losing marks. But for the most part, the idea, the paradigm I'm going with is you get awarded marks. The interesting thing is, what does it add up to? I can't remember. It's either, does it say what I have it up to? All right, it doesn't, but it's fine. So assignment 2, same idea. Assignment 3, same idea. There's a final project, same idea. Participation, same idea. Whatever. And then the lecture, maximum 10, that'll kind of be marked, but that's optional. One thing you'll notice is the sum of all the potential marks you could get is like 130, 135 or something. If you get technically 99, because we can't give 100% at St. Effects because whoever programmed the system is hilariously stupid. Because it only gives you 2 digits. So if you get 100, too bad, you got 99. So dumb. If you get 99 points, you'll get 99 in the class. The sum of your points will be your final grade. What's interesting about this is it gives you the ability to pick and choose. I mean, it gives you the ability to make mistakes. That's a good thing. We like mistakes. That's where we learn. It's computer science. Most of what we do is make mistakes. And then we spend hours trying to fix those mistakes. So you're used to that. But it gives you the ability to pick and choose. If you say, I really don't want to give the lecture, that's fine. You do have to do the final project. How I'm going to have that set up, I still don't quite know yet. Because all of my plans from the previous years don't work when the class is 3 times larger than it was. Technically, the class is way bigger than that. Because last year, or the last time it was offered, it was only 340. Or no, it was 340 and 547. There were only 6 undergrads. So now we've got like 45 undergrads or something in the course, which is awesome. But some of the original stuff won't work as is, so there might be some. I'll let you know how everything's going to work out. So you don't have to do the lecture, but if you do, you can get a bunch of points. You could just say I'm not going to do assignment 2. All right, whatever. You can decide today roughly what your final mark is going to be. If you're going to be happy with 50 in the course, you can figure out what you're going to do right now, how to get your 50. I don't care. Fine by me. It's slightly modified from last time. It was very, very, very popular last time. The students really liked this. The graduate students didn't. But that was our first cohort of the applied master's students. and there was some hiccups. So yeah, any questions about this idea? It's all right if it's unclear. I'll expect you to have questions later because this is very atypical from what you're used to. But the spirit is, I don't want to take marks away from mistakes. That's stupid, right? Like what I want to do is give you marks for doing more, for learning more. That's the idea. So that's why it's like, well, okay, if you do a write-up with good statistics because you had to go and learn how to do the statistics and how to make that comparison, wonderful, that's fantastic. And then you figured it out for assignment 1. Well, now it'll be really easy for assignment 2 because you already know how to do it, right? So that's the idea. And it gives you the freedom to pick and choose. I upped the total number of marks this year. Hopefully that doesn't mean everyone gets 100 or something, but whatever. I'll explain that one later. Any questions about any of this? All right, cool. All right, and this right here is just that same PDF. Oh, no, it's not. It's the old version. Don't look at this one. This one's bad. The real one is posted online on Moodle. But yeah, you will see. Oh, this is. I don't know. You'll see this is out of 25. Well, this year it's out of 30. So yeah, just note that the ones in the slide currently are out of date. The real one is the one that goes with the syllabus online. Mark breakdown. Yeah, you gain. Yeah. Oh, that's old too. There's like 130 or something now. Yeah. Okay, everyone, final. Yeah. Okay. Mark breakdown. Pick what you want. Everyone will do a final project. Topics and enhancements will be decided by the students in consultation with the prof. Yeah, so for your final project, it's do whatever you want, but like in consultation with me, I might make a group project or something, I don't know. There's a lot of students, and that'd be a lot of projects. And these projects tend to be big. But yeah, we'll figure out your topics and whatnot a little later in the course. Hopefully, earlier is better because then it gives you time to do it, of course, but we want to make sure it's far enough in the semester that you kind of get a sense of what there is that you could do. So we'll have to balance that. The lecture, each student may give a lecture. It used to say must, but now may. This will just like early in the semester, we'll say, okay, who wants to do a lecture? And the lectures will only be like 20 minutes, I think. Or 15 minutes and 5 minutes for questions. And it'll be on like a specific topic of your choice with consultation with me. We'll have you decide if you want to do one of these earlier because then it helps with planning the rest of the course. I would say, like I mark the lectures easy, so I encourage you to do it. But if all 45 people want to do a lecture, so it might be a first come, first serve. So let me know if you want to do a lecture sooner rather than later. Yeah.
Can I do a lecture?
Sure, but email me. I might make something on Moodle where it's like, add your name to this list if you want to do it. I'll find a way to make it consistent or something. And I'll set a deadline for when it needs to be in by. Attendance. I'm supposed to take attendance. I own everything unless it's from the textbook, and then they own all that stuff. You're not allowed to make recordings of me, but I do that myself, so these will be posted to YouTube, so you don't have to. So I own everything. Don't cheat. Who here knows how I feel about cheating? For those of you that don't know, I love catching cheaters. In fact, last time I taught this course, it was the graduate section that had a lot of cheaters. I really got to be detective that day. Or that semester. It was a lot of fun. Because I caught someone who cheated only because what they did is they copy and pasted from a website their whole report. Okay? And within it, they copy and pasted some like mathematical notation, but the mathematical notation from the website used like a markup language, logic, okay, to get all the fancy symbols. But when you paste that into Microsoft Word, you don't get the fancy symbols. You just get all the markup language stuff like /math, / bit, you know, whatever. So I saw that and thought, well, that's weird. So then I found another student that had a remarkably similar write-up, but I knew the students were kind of like friends, and you know, if you're working on a write-up together and some of the same ideas are popping up, yeah, okay, I get that. But it was a little too similar, and then there was like a third student that did it too. And actually, it was the third student that had the LaTeX markup language in it. And when I got to that third student, I was like, this is weird. So I just opened up Google, pasted the LaTeX thing, and boom, there's a website with this markup language exactly verbatim right there. But the funny thing is, it was in a different language. All the writing was in a completely different language. So fortunately, Google's like, hey, you want to translate this page? And I said, sure. And there it was. Oh, I was so happy that day. Because I was like, gotcha, yeah. There were a bunch of cheaters that year. Anyways, don't cheat. I'll catch ya. I'll use Moss. You know, I don't catch people that don't cheat. I catch cheaters. So, yeah. But again, it's really easy not to cheat, so it won't matter, right? And also, I don't believe in the crap where it's like, oh, you know, when you get caught cheating, it's not about punishing. It's about teaching. Bullshit. What is there to learn about cheating that you didn't get taught when you were this big, right? It's the same rules. Oh, I didn't cheat. I only gave my assignment to them. Are you kidding me? What? Don't cheat. I'll catch you. And you all know, well, a lot of you know how much joy I get out of it. So, I mean, you'll make me happy in the wrong way. Yeah, don't cheat, don't cheat, don't cheat. You can email me, whatever, yeah. Read the syllabus, yeah. The syllabus is on Moodle. As with all my other courses that a bunch of you have ever taken with me, you can email me questions, I'm happy with that. But as you know, when the questions start to get like big, don't email me those questions. That's an office hours question because I won't be able to spend the 20 minutes it takes to answer every one of those emails. It's not possible. There's not enough hours in the day. If you email me with like a simple question that you think, and I respond saying like, you know what, come to office hours, that's not because I'm like saying, oh, you blew it, you asked a question that you shouldn't have via email. No, that's just because it may seem like a simple question, but the explanation might be very nuanced, so email's not a great place for it. Yeah. Office hours are virtual. There's a Moodle link there to Blackboard Collaborate. It says like, oh, 161. I'm just using the same place. So, yeah. Office hours is for all of the students, regardless of what course you're in. So, yeah. So when you see 161, don't worry, you're in the right place. Yeah, so there's that. Okay. Nope, not that one. This one. Okay, don't show again. All right. See this right here. Wait, what does the slide say? Evolutionary computation. This right here is the basic high-level idea of almost all different forms of evolutionary computation. What you do is you start with some initialization. Imagine there's a problem I want to solve, and with evolutionary computation, we tend to use it to solve very, 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 very hard problems. You don't use it when there's an alternative that's better and easier. This is the type of stuff. Evolutionary computation is in the class of algorithms that we call computational intelligence. And the things within that class, these are the algorithms that you don't want to use. Okay? In that class are also neural networks and a variety of other things. These are the type of algorithms that you really don't want to have to use. You want to be solving problems that don't need these things. Realistically, of course you might want to solve some of those problems, like self-driving cars, right? But if you get a problem that you just want to solve real quick, you're going to hope you don't need a form of computational intelligence. Computational intelligence is what you use when you go, well, we got nothing else to do, so we just throw the howitzer at it and hope for the best. But there are little problems out there that throwing a howitzer at might be kind of useless. A howitzer is like a big old World War II cannon thing. So it's in the class of very complex problems. So we can imagine, and there's a little website I'll go to show you. Imagine I have this two-dimensional, you know what, no, I'll start by showing that website, and then I'll explain. I think this is the one I want. Perfect. So what this is doing is evolving. Actually, it started with a really good one. I'm gonna refresh it. That's too good to start. So, right here we have 20 randomly generated cars. And the purpose is these little cars are going to traverse this two-dimensional space. Wow, look at that one go. It's going to traverse this two-dimensional space to try to get as far as it can. This one's crushing it. But it will get stuck eventually because this, look at that, it got bottomed out. When we start to solve a problem like this, you know, if I told you, build a car to work on this, you might be able to whip something up. But here's the idea. Let's start with 20 randomly generated cars. Do we expect those to be any good? No. But we saw that some are better than others, right? Better at traversing that space. But most are garbage. But the idea is, what if I take the good ones, change them up just a little bit, and try again. And again, and again, and again, and again, and again, and again. And we'll let this run forever. Eventually, we get tired and we hit stop. And at the end, a lot of times we end up with really good cars that are pretty good at traversing the space. I don't think that this runs when I don't have it in focus, so I won't be able to, maybe it does. Let's see, is it still in the air? Yeah, it is. So I won't be able to let it run while it's not in focus. But that's, no, wrong set of slides. There. So here's the idea. We initialize. We randomly generate a bunch of cars. We evaluate them somehow, let them drive. We select good ones, relatively good ones, vary them a little bit, and evaluate them again. And so on, and just loop. Until we're like, all right, fine, we're done. Termination can be decided from a variety of ways. That's the general idea. That's basically the whole course. That's all we're going to talk about, is that. We're going to talk modifications on that. We're going to dig into each thing, of course. But that's basically it. That's the idea. That's the idea of evolutionary computation, that. It might sound like that's stupid. No, it works weirdly, and it's fantastic. There are certain problems out there that evolutionary computation has been used to come up with the most mind-blowing solutions to the problem that no one would ever figure out. No engineer would sit down and design. But evolutionary computation came up with a solution that's now an antenna on a satellite. There are rumors that, it's just rumors. There are rumors. Who here is familiar with like the Black Hawk spy plane? A couple people. You've probably seen pictures of it. It's like that long plane that was used for taking pictures. It's really fast. There are, and it's like not, sonar doesn't work on it or something too, I think. There are rumors that it was designed with evolutionary computation, but no one really knows because, top secret, right? So evolutionary computation is really neat, but we use it to solve problems that are complicated. Okay, are there any questions so far? You all know how I like to teach. I don't like to just talk at you for an hour. I like questions. Yeah?
For evaluation methods, you can use pretty much anything, right?
As long as it makes sense in the context, and we will look at a couple of examples of a certain problem and different evaluation metrics we could use, and what are some pros and cons of each. And then we'll also talk about multi-objective stuff, where you have multiple criteria you want to optimize. I mean, one of the toy examples that we always talk about in evolutionary computation is factory productivity and worker deaths. So we want to make sure we maximize the productivity of our factories, but minimize the number of deaths. But how do you know what the best option is? Because you'll end up with something called like a curve, right? Where it's like, well, I do have markers somewhere. Yeah, you'll have like a curve like this, where you can have like, what do I want here? Number of deaths. No, this is a bad one. This would be, how would this one work? If I have number of deaths and like efficiency, what we'll probably see is maybe a curve that looks something like this, right? Well, you know, we can start to get pretty efficient, but a bunch of people are going to die. But we might be really inefficient, but no one's going to die. So someone needs to decide what is an acceptable level of death in their factories, right? The evil pig has got to go, all right, well, you know, realistically, I mean, it seems to taper off here, so let's go with this many deaths. And we're going to be pretty productive, and I mean, we don't need to kill more people to get any more productive, really. So, yeah.
So where on that chart is this class?
Okay, that was amazing. Very well done. Very, very, very well done. That was a good one. I don't know. I'd say probably around here or something. You heard what they did in Ontario, right? They have phase 3 reopening, but you have to have all social distancing, and there's these limits on classrooms. But the Ontario universities lobbied the government to have all the social, like all those constraints not apply in learning spaces, meaning you can pack 500 people into one room. So everyone's like, well, the good news is COVID doesn't come on the university campuses. So that's great. But the funny thing is it only applies to learning spaces, so everywhere else on campus, like office hours, we would need to be socially distanced. So anyways, we're all making it up as we go, I guess. If only there was time for some planning beforehand, you know? If only we had some sort of insight into potential issues coming up this semester. But I guess there was no reason to believe that there'd be any potential issues this semester. So that's why there was no planning and preparation for anything, right? Must have been the case. Any other questions? All right, cool. I almost want to end on that high note, though. All right. Okay. So before we can even talk about evolutionary computation, we need to take a second and think about, like, what are problems? Are there different types of problems? What are we going here? Like, raise your hand if you've taken a machine learning class. Raise your hand if you've taken like an AI course or anything. So not everyone, though. The point is, we might even really be at a stage where we can talk about like, well, how we want to go about trying to solve some of these problems. Pardon me for 1 moment. There we go. So we're going to talk about problems, optimization, modeling, simulation, search problems, optimization, constraint handling, and hardness. Who here has taken theory of computation? Okay, cool. So a lot of times we like to think of systems in this sort of way. got some model. We can think of it as a function. Just think of a function in Python or something. So we have this model that is designed to model something. Okay? Maybe it's to calculate a grocery bill. You know, whatever. We have some input and then output. Not always, but a lot of times this is the case for it. So we've got this model, this function. The input could be the groceries that they want to buy, and the output is their bill after tax. Right? Not a crazy idea. Fairly straightforward, but this is just how I want us to think about this right now. So we think of it as a box. Sometimes we have these black box models. Sometimes we have these white, clear, glass, whatever word you want to use, like white box models that you can see into and you can understand. Like that function for calculating your grocery bill. You can look at the code and be like, yeah, that makes sense. But there are certain models out there that are just so complex that we don't actually really know what's going on in there, but we know they work well. Good examples of that would be like deep learning. People will say like, no, it's not a black box. We know that. They're lying to you. There are black box models that are really good, but sometimes they're not workable in certain situations. The classic example of this is, if I use deep learning to make YouTube video recommendations, and then my boss comes to me and says, but how does it work? Like, why did you suggest to show this video after? And if my response is, I don't know, but it made us another $1 billion, my boss is going to go, good, right? But if I've got this thing that is telling physicians that they need to go get neurosurgery, right? And the physician says, yeah, but why? I can't just say, well, because I gave the data to my magic box, and it's right a lot of the time, so you should do it. The physician's going to go, no, like that's not working. Right? So sometimes black box is fine, sometimes it's not. It depends. So the model, we can think of it as a function. I mean, we could model counting by 1 as just like, okay, the mathematical function f of x equals x plus 1. You know, and just keep pumping it into itself. Like the model can be anything, right? And model is an overused word to kind of mean whatever we want it to mean. And in this scenario, I really am using it that way. We are modeling something. But we're going to talk about specific examples shortly. So yeah, in computer science, we often take something from the real world, in vivo, to use fancy Latin, and try to model it in our computers, in silico, which is not really Latin, but it's a Latin-sounding thing that people came up with to sound more scientific. And models can have different types of input, like numeric text, yeah.
Is that what they call it, Silicon Valley?
Well, they're just called...
Just the name of the place.
No, they call it Silicon Valley because semiconductors, silicon's one of the, so yeah, it's connected. And that's where silico comes from. They're like, oh, in silico. But that would, like, Latin people didn't, like, ancient Romans didn't use that word. So yeah, numeric text. And models can be simple or complex. But if we know the model, if we have the correct model by whatever metric we want, if we have the correct model, we can compute the input for any or output for any valid input, right? I could probably come up with a perfectly correct model of calculating the grocery bill. And with any input that's valid, it'll output the correct output, right? With something like that neurosurgery thing, I have a model. I can't prove it's correct, but I can demonstrate empirically that I've run it 1 billion times and it's correct 99.99999% of the time, right? But I can't ever really say that, like, oh, if I have the input, I can give you the correct output. I can only ever say, like, I'm really confident in this, but there's always a chance, right? Model. Add up the values then apply the tax calculation. There. Okay? Groceries come in, your bill comes out. This would not be a good model. Randomly add or subtract the values and then divide by the tax percentage. That's not good. That's bad. This might feel like really, yeah, obviously, I understand. But the only reason I'm doing this is to make sure that we understand our terms and how we like to think, okay, input, model, output. Input, function, output. So, how do we find a good model? Well, that's the problem. A lot of time, this is going to be what we care about in this course. You looking for me?
Calculus?
No. Good luck. So sometimes we might have a model that we know is correct. We know how to calculate something with our model. But what I want to do is optimize. I want to find the input that when it goes through my model gives me the optimal output. Or something close to that, because maybe finding the optimum is impossible. Or very, 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 very difficult that we would never assert that it's the optimal, but we would just go like, well, we're pretty happy with this result. For example, recommending YouTube videos. It might not be perfect. In fact, I don't know, but anyone else feel like it's gotten recently crappier?
It's always been horrible.
Well, it has, but lately it's like recommending like, what's his name? What's Tucker Carlson to me? I'm like, why is this happening? Like, why does it want me to watch this? Anyways, we want to optimize the output. So when optimizing, we know the model, we know the output. Better keep an eye on the time, eh? Oh, we're in great shape. What we want to do is search the space of possible inputs to find a good output. So raise your hand if you've ever heard of the traveling salesman problem. I talk about it sometimes, but I'll go over it again. Yeah, I stole it from Wikipedia. Imagine you needed to visit all these cities, right? In your aquatic car. Because you want to, like, you know, we're starting in, I don't know, let's say we're starting in Toronto because it appears to be there, okay? And Halifax isn't included, so we'll use, maybe let's see, let's start in Toronto. The goal is we need to visit every single one of these cities. We're going to start in Toronto and we have to end in Toronto. And I want to visit every single one of these cities in the shortest possible way, right? So this right here looks like a pretty good traversal, right? Okay, we're starting in Toronto, then it looks like we're going to Buffalo, and then, I don't know, Kingston maybe. I don't know what's over there. Rochester? Ottawa? Montreal? I don't know. Whatever. I'm making it up. I don't know. Point is, there's the order. What you wouldn't do is you wouldn't go like, well, first I'm going to go from Toronto, and then I'm going to go to Miami, and then I'm going to go to Hawaii, and then I'm going to go to Calgary, and then I'm going to go to somewhere in Texas. Like, you wouldn't do that because you're backtracking a lot. You're covering the same ground. So we want to find the path that is the shortest possible path. So in this case, the inputs are every possible permutation of these cities, where the permutation is the order in which you visit the cities. Start at Toronto, then go to Buffalo, then go to, and so on and so on and so on. So that's what we're looking for. Now, this goes a little bit to talk, like from here we can talk a little bit about representation. How do we want to encode these cities? A good encoding would be a permutation. But let's say I label cities 1 through, I don't know, 100. I don't know how many cities there are in here. Probably not 100, but let's say there's 100. I could label each one to a number 1 to 100, 0 to 99. I don't need to call them by that. We could just randomly pick numbers between 0 and 99 to come up with like an ordering, right? But if we do that, we're at risk of having duplicates. Meaning go to Toronto, then Buffalo, then Toronto, and then Buffalo, and then, I don't know, somewhere else, and then so that encoding isn't great because it would allow for stuff that we know would be not admissible because we need to visit every city. So we can come up with a better encoding, a permutation. Make sure each value is unique. Done. Does anyone know how many permutations of 100 cities there are? A lot. Well, let's have a quick look. 100 factorial divided by 2 minus 100 minus 1 factorial divided by 2. The reason it's minus 1 is we always start in the same city and end in the same city. And then we divide by 2 because forward and backwards are the same. Don't worry. It's going to be along the lines of 100 factorial. Why? Well, if we have, and I realize we're running out of time. If I start at city 1, okay, how many other options are there? 90, okay, so I have like 99. Okay, so then I pick the next one. I guess it really would be, yeah, okay. So let's pick the next one. How many do I have to choose from? Then how many? Right? That's just factorial. Because we pick one, and then how many more options do we have? So we multiply it out. So it's factorial. So what's 100 factorial? 9.33 times 10 to the 157. That's a big number. There's 157 zeros. How many atoms are there in the universe? The number of hydrogen, which is the most common one, is times 10 to the 82. You could take listen carefully to this, because this is big. Us as humans, we are really bad at big numbers, at wrapping our head around what it means. What this means is, we could take every single permutation of 100 cities, every possible one, and assign it to each atom, each particle in our universe. And we'd run out of particles. Isn't that crazy? That's crazy, right? Now, the funny thing here is, the model for calculating this is trivial. All you have to do is, you give me a permutation, calculate the total distance it would take, and that's the total distance. Would you agree that if I took every single possible permutation, calculated all their distances, and just pick the one with the shortest distance, would you agree that that guarantees me the optimal solution? Yeah, of course it does. The problem with that is, I'm not doing that. It would take longer than the universe has existed to calculate all of them. This is a great example of where computational intelligence comes up. Now, there is an actual good, clever approximation algorithm for something like this. But when you're dealing with a problem like that, one, we go, okay, we're not worried about finding the optimal. If we get it, great. What I care about is getting a good solution, right? That I can get quicker than trillions of years. So that's traveling salesman problem. And I think we're out of time. Yeah, we're out of time. Anyways, we'll pick up here next time.